So, hi everyone. It is my pleasure to welcome you again at this New Year's session for the CosmoVerse Journal Club. Our first speaker today is going to be Facundo Toscano, a PhD student based at the University of Cordoba in Argentina. And today he'll be telling us more about CMB, how CMB-derived cosmological parameters can be affected by foregrounds of galaxies. So please, Toscano, Facundo, feel free to start whenever you're ready.
Okay, thank you, Enrico. Thank you, Maddie, also for the invitation. I am, as Enrico said, I am from Cordoba, from the National University of Cordoba. I am working in CONICET and in the Institute of Theoretical and Experimental Astronomy here in Cordoba. And today I will talk about this paper that we published in 2024 about how the nearby galaxies that our group have found that have negative temperature signals on the CMB affect the cosmological parameters, the derivation of the cosmological parameters using the CMB. It was done with Diego Garcia Lambas, my advisor, from the Hansen, which is a researcher from Norway that have worked almost 20 years in Planck collaborations, and also Eliana Luparello, which is also from Cordoba, Pablo Fosalva and Enrique Castañaga, which are researchers from Barcelona. So the idea of this talk and this paper is that if you estimate the cosmological parameters, as a lot of people know, you have the tensions, basically the H naught and sigma tensions. And if you use the early universe to estimate the cosmological parameters, basically the H naught, we will talk in this plot of H naught. If you use Planck or Big Bang nucleosynthesis or BAO, you obtain a value of 67, more or less, which with an uncertainty of 0.5. But if you use the late universe tracers as supernovae, as masers, or TRGB, you obtain a value of 73, more or less, with the uncertainty of 1 plus minus 1. So there is a 5 sigma tension between the results because they are very precise. The community don't know and are working on why this tension is there. And also there exists a tension on sigma A, the matter fluctuation of the universe is less than 5 sigma, but it's also tension. In that context, in 2022, our group started to study an effect of very nearby galaxies on the local universe that seems to have an effect on the CMB data. When you use that galaxies as tracers on the CMB, you see that the temperature profiles around that galaxies are negative. And it was unexpected. It was statistically significant, but we don't know why this effect is happening. So one idea was, okay, if we have these galaxies that are changing the CMB data, the CMB temperature data, and we know there exists a cosmological tension, what happens if these galaxies are changing the values of the cosmological parameters? So our idea was to take into account these galaxies and study the effect on the cosmological parameters. To do that, we can go through a masking method, mask the galaxies and study the effect of the rest of the sky that we have, or correcting the galaxies effect, okay, the galaxy effect on the CMB. But for do that, we need a physical motivated model. And at that moment, we didn't know why these galaxies were changing the CMB temperature. So it's more difficult to have a physical motivated model if you don't know the physics that is happening there. But the idea is to use this new extragalactic foreground to see if we can construct a bridge between the early root and late root, or to see if there is new estimations there that solve the tensions, at least in some sigmas. So the idea of the talk and of the paper is to see this, if this happening or not. So I'm going to start with the new extragalactic foreground. What is that? As I said before, we started in the late 2022 and with this paper in 2023 of Luparello, Eliana Luparello, where we saw that the spiral galaxies, basically, of the two emergence galaxy distribution have an unexpected negative temperature signal on the CFB maps. If you see here, you have the temperature profiles using the galaxies as tracers. Okay, we use the coordinates of these galaxies to make a temperature profile around that galaxy on the CMB map. Okay, we are using only the positions of the galaxies, but the galaxies have effect, as we know, all the structure on the late universe have effect on the CMB because you have all the effects interiorities as well. You have Sunai-Sedovich, for example, Reshama, and a lot of effects due to the structure. So seeing that, we obtain that the temperature profiles around the large spiral galaxies and also the high density spiral galaxies, the high density environments, the spiral galaxies that were on the high density environments have a minus 20 in amplitude microkelvin of effect compared to the random positions on the CMB maps. Okay, this is random simulations using positions that are not galaxy. Basically the cosmic variance of the CMB. And we saw that the galaxies, the spiral galaxies, as you can see here, is very tiny, but the ellipticals don't have that effect. But the spiral galaxies in the center of the galaxy have an effect of minus 15. Okay. Then in Hansen 2023, we also saw that these galaxies, this galactic foreground map, if you want to say like that, have very correlation, is very correlated with the lowest multiple of the CMB. This is L2, L3, L4, and L5 of the CMB, and this is the same multiples of the galactic foreground map. You can see that there is some correlation. Then in another works and with the years, we saw that almost all the power of our foreground signal is in the lowest multiple. We say and up to L32, more or less, which is a problem also because we know that the lowest multiple of the CMB are very have a great noise, are not in concordance with the model. But we noticed that, and also we noticed that the galaxy size of the galaxy size of the spirals that we are looking for change the amplitude of the profile. Bigger the galaxy, higher the profile, higher in negative temperatures. No, and we made toy model, okay, for this galaxy, but we still not knowing what is the cause of this effect. And one important thing of this effect is that it didn't change with the frequency of the CMB map. The Planck CMB data have different frequencies: 100 gigahertz, 143, and 217, and 353, and others. If we use each map, each frequency, and look the effect in that frequency, it didn't change. So we start to think that it's not a effect of a particle and a scattering effect, because we think that we thought that if was an effect of a particle and scattering effect, we had to see different signals on the different frequencies, and we see the same effect in all the frequencies. So the idea was that this is a gravitational effect related with dark matter or dark energy, or we don't know. And also with the different papers that we have done, we saw that the filaments have this effect. As you can see here, the regions with higher significance with respect to the CMB simulations, for example, this one is almost phi sigma with respect to 10,000 CMB simulations, Planck CMB simulations, are related with regions where the massive filaments on the local universe are located. As you can see here, this is all the filaments of the redshift range 0.004 to 0.02. It's very, very nearby. These are all the filaments, and these are the massive filaments in that region. So we start to think that it's an effect related to overdense regions more than galaxies. And the last work that we have done is that in the subdense regions, I mean the void, we have the same effect with a positive profile, the opposite effect. But in that moment, in the moment that we make this paper with the parameters, we only know the galaxy effect. So we start to think what happened with these galaxies. Can these decrements in the CMB temperature map impact on cosmological parameters? So as I said before, you have two ways to go there. Quantitative model with a foreground physical model, or a qualitative solution, masking, and with simple toy model, phenomenological model. And that was that we have in that moment. So we go with that approach, with a masking method to study the cosmological parameters, to see if they change or not, with all the things, the issues that have that kind of solution that we are looking for. So for the cosmological parameter analysis, we use the Planck data using the pipeline PR4, the NPipe, the last data that we have from Planck. We mask all the 2MRS galaxies that we know that have that effect in different redshift range, but basically from 0.004 to 0.03, more or less. We use the multiple range from 32 to 2000. We cut the first multiples, the first 32 multiples, because we want to use a Gaussian likelihood, and also because that multiples have a huge uncertainty. So we are masking the CMB data, the 67 fraction of sky, we are masking that sky fraction. So we are having less than 60% of the sky fraction. So we increase the uncertainty. So if even increasing the uncertainty, we also use the lowest multiple with huge uncertainty, we will not obtain nothing. So we take into account that, and we say, okay, we have to cut the first multiples, and we start in 32, go to 2000 with a beginning of 30 multiples to have a covariance matrix, which is diagonal. We didn't use MCMC to estimate the parameters because we have some models to test and also different masks to test. So for time, we use only a minimizer, Immunoid, which looks for the best fit cosmological parameter. And we use the 600 publicly available simulations of 7 to study the error estimation, the error of the parameters. We run the pipeline with the 600 simulations, and we estimate an error of the real data. We test our pipeline with PR3, with Planck public release 3, only using the temperature spectrum. We obtain almost the same, and we use these three different masks. The difference in this mask are basically the masking patch size. I mean the distance that we are masking around the center of the galaxy that we are using as tracer. More or less is 2 megaparsecs, in others is 4 megaparsecs, depending the redshift range. But a typical size of a galaxy, of a halo of a galaxy, is 200 kiloparsecs, so we are masking more than a galaxy. We are not seeing the galaxy at all. We are masking the galaxy, we are masking the halo of the galaxy, more than the halo, beyond the halo of the galaxy. And we are seeing the cosmological parameters in the available fraction of sky that we have, which is around 60% here, and here is like 50%. Okay. What we obtain these parameters we will focus on H naught and sigma A, which is derived from omega c H squared. And there are basically there are not statistically significant difference with respect to the results of Planck. Okay, only using the temperature spectrum. Okay, so why? Basically, because it's a coarse method. We are masking the galaxy only. We are not seeing the high multiples that could affect the cosmological parameter determinations. And we are not seeing the effect on the center of the galaxy that, as I show in the previous slide, is very huge because the temperature profile, has minus 20 in the center of the galaxy. Okay, and we are masking all that information, but also because most of the signal of the foreground signal is in the low multiples, as I showed before, is in the L2, L3, L4, and L5. So with that information and with this in mind, we say, okay, what we can do with this information? We know that there is an issue with this foreground, but with the tools that we have, we cannot say that it's significant for the cosmological parameters. So we start to think in a paper of 2021 from Fosalva and Gastañaga, where they found three regions that they call horizons in the CMB with very different values of the cosmological parameters with respect to the mean cosmological CMB values. Okay, the mean CMB cosmological parameter values. These regions, two of these regions, are in concordance with our foreground galaxy distribution. These regions are these red circles here. This is one, this is another one. And they're in the blue dots or the blue spots are our galaxies, okay, with the negative profiles of the in the CMB. And you can see here that they're in very concordance. So the idea was to study if our galaxies really correlate with these regions that Fosalva Castaneda found. We will focus only in H naught and omega c H squared, which is a proxy of sigma A. And the idea was to study if there is a real correlation with significance in these regions, because maybe they say anything or something about the cosmological parameters. More important is that in that regions, the H1 and H3, the cosmological parameter values are higher even than the supernovae values, 76 and 75, more or less. So it's interesting to see if it were or not correlation, because it will talk about regions where the cosmological parameters are very, very different to the CMB cosmological parameter values. So, do these maps correlate or not? Okay, we calculate the correlation between three different phenomenological models for our foreign galaxies with the H naught and omega c H squared parameter maps. This model basically changed in the smoothing scale, as you can see here. They're more or less the same because they're tracing our galaxies and the galaxies were the same, but with a change in the smoothing scales. This is more smoothed, this is less smoothed. And we estimate the correlations, and then we estimate the uncertainties using these three models versus the simulations, CMB simulation, in the same method that they study the parameter variations, and the CMB data versus mocks of our galaxies. This is some usual CMB simulations of H naught and omega c H squared, and these are mocks of our data. This is the real catalog, and this is three mocks of the real data using a mock of the GMRS. And we obtain that the correlation is about 0.4, 40% of correlation, which is less than the half, but with a significance of, in this case, more than 3 sigma, in this case, 2.5 sigma. In both cases, using simulation versus data or using mock versus CMB data, we obtain almost the same. So we say, okay, it's a correlation, it exists. But the idea of Facundo Toscano was to construct 60 degrees circles on the sky. 60 degrees circles is correspond to L equal to 3. So maybe all the information is related to the first multiples that we know on the CMB. They have problem. So what's happening if we remove the lowest multiple? So we remove up to the quadruple, up to the octuple, and we perform the same analysis. If you remember, we use the model 3, I put here the model 2, sorry, but they're almost the same. This is dominated by the quadruple. If you see here, it's like 1, 2, 3, 4. It's more or less a dipole and a quadruple. Removing the quadruple, you have this structure also in the foreground model. And removing the octuple, you see that the octuple is basically 0 because they are not changed between one and another. These are the maps, the parameter variation maps. These are the CMB maps. This is our model. And we made the correlation. What we obtain is that the correlation, the power of the correlation is lower, expected because you are losing power, but the significance is higher, more than 3 sigma level in all the cases with H naught and omega c H squared. This is removing up to the quadruple, this is removing up to the octuple. More or less in both the cases, it's the same. But we are seeing a real significant correlation in the CMB of regions that have parameters higher than the supernovae values, very, very different to the CMB mean values, and regions of the sky, of the local universe, that have negative temperature profiles. And that is what I want to finish with that, is that, okay, we didn't found that the cosmological parameter changed because we are using a method that is not the best method to study that. But for sure that exists an issue with these galaxies because they are very, very correlated with regions on the sky that have very different values of the cosmological parameters. How that regions could affect the mean CMB estimation of the cosmological parameters is something that we are studying because really at that moment I didn't know how, if you study circles of 60 degrees and you change the cosmological parameters in different circles and in different places, how all the spectrum could change or not. So we are studying that, but basically we are we are thinking that exists a correlation with our galaxies that are changing the cosmological parameters in some way that really we don't know. So, a reached new estimation? Not yet, but we are looking for that. So, thank you.
Right, thank you, Facundo, for your very nice presentation.